understand you guys are doing like a big exascale like training death march here, and what I'd like to do is just share a little bit of perspective from probably the guy with the most gray hair in the room. So that'll be the first maybe 10 or a dozen minutes just to kind of set the stage for where for then the second part. Let's sit back here because I should have a clicker. So there's a really long history of leadership in high-performance computing in DOE. It literally goes back to the beginning, to people designing bombs in World War II. John von Neumann, you think of the von Neumann architecture, he was the head of the Atomic Energy Commission, right? So, you know, it basically goes back to the beginning. It continues today. And it's not just, you know, buying big machines or buying the first copy of machines. It's then, you know, being pioneers in all these science and engineering domains and the mathematics and computer science that underlies it. So you guys are kind of joining a tradition that's half a century old of really, you know, intellectual leadership across a broad range of sort of high-end computing, you know, topics. So when I was your age and there was hair on top of my head, then it was really an exciting time because, you know, people. Actually, here's an interesting thought. You think of CMOS, we forget that it's CMOS FET, right? So the idea of a field effect transistor goes back to the mid-20s, right? So it wasn't until the early 80s before we could really make CMOS, and really be late 80s before we could make it reliably. So there was a technology detour. The transistors that were invented in the late 40s weren't the transistors people had been trying for a quarter century to make, but rather were PN junction devices. And so, you know, humanity ran with those things, you know, for 2-3 decades. So 30 years ago, you know, the sort of the reliability and performance of you know, field effect transistors was finally looking like they were going to pass, you know, the other guys. And so you could see this killer micros, you know, coming. This is a picture of an old ECL mainframe, beautiful machine. And this was a, you know, little Intel, you know, probably PMOS in those days chip. Anyway, so there's a huge period of uncertainty. Lots and lots of people, often spinning out of places like MIT or Caltech, propose new machine designs. You know, I programmed the BBN one. Paul had the Touchstone Delta at Caltech. I programmed the Thinking Machines 2. There should be a CM5 on there. There's not. My favorite of this bunch was the Cray T3E. That programmed the C90 and the N-Cube. So it was really an exciting time to be sort of a young person in sort of high-end computing because you didn't know what the future was, and there were lots of fun playthings with different programming languages. You had to rethink all your algorithms every time you hit a new machine, which might be every few months. It was an exciting, very exciting time. Mid-90s, maybe 94, 95, we hit a stable point. So no more ECL or exotic circuit technology, basically using the same fundamental technology that was in mass production PCs. Distributed memory architecture, which makes it basically easier on the people building the system. I think it was a false economy because it makes it harder on the people programming the system. And as time has gone by, you know, the value of labor has become increasingly important in sort of this enterprise. And this thing called the Beowulf, you've heard that term for PC clusters. That's sort of the epitome. That's Tom Sterling who coined the name. I think that was his third Beowulf at Caltech. Anyway, so all off-the-shelf components, you know, Linux, so, you know, free operating system if you're capable of installing it yourself. And a funny thing about that is no one has any clue how many, you know, Beowulf-type machines are out there in the world right now. It's like dark matter in the universe, right? Because if you go to the hardware store or an electronics store and buy a bunch of PCs, no one knows if you're setting up a small office or building yourself a Beowulf. In fact, I have a story from Boeing. An engineer wanted a big computer. His managers tell him, you are unworthy of such a thing. Go off and do your job. And he figured out that as an engineer, he could buy office equipment, and PCs are office equipment. So he bought a lot of office equipment, and his managers have no idea how he got his job done. Okay, so that's kind of, and in some sense, I would argue that things like Titan and Mira, you know, they're sort of the evolution, you know, of this same thing over the last, maybe more Mira than Titan, but the evolution of the same thing for the last 20 years. People here, in particular at Argonne, made huge contributions. Again, you know, the DOE HPC community made huge contributions. Here's a shopping list. the basic programming model, the reference implementation was done at Argonne. The work continues at Argonne and other places. New mathematics, libraries to implement all this stuff, and system software. Often you buy a machine, but you install your own system software. Everyone's heard of Moore's Law. The top line there is Moore's Law. Basically, what Gordon Moore said was that he could double the number of transistors he could profitably sell to you every 18 months. It had nothing to do with performance, just more transistors. So another guy named Dennard, who was at IBM, he's also the guy who conceived of the DRAM. Dennard figured out how to scale basically MOS technologies. So as you scaled the line widths, you'd scale the thickness as well of the oxides, and you reduce the voltage. And the net result is you could have, not only did Gordon Moore give you more transistors, but Dennard gave you more performance. And so it was a wonderful time, basically from when these things first became reliable. Continuing, there might be another decade of Moore's Law ahead of us. I mean, at some point, you get your line widths are an atom. That's ridiculous, right? But Intel thinks they'll get down 5-6 nanometers for sure. So this is still cooking. But the Dennard scaling, that's over. So they can't make silicon dioxide any thinner. You can maybe get lucky and find hafnium oxide or something like that, and maybe buy a generation. But you can't make the oxides thinner, and the voltages are already down close to the threshold voltage, so that's not likely to change. So anyway, so the Dennard scaling's over. That means power per processor is going up. So we stop that by flattening the frequencies. That stops the power problem. It also stops single thread performance. So for most of your lives, as far as you can remember, PCs have been about the same speed for any one arbitrary application, right? And you get more cores, and the whole ensemble runs faster, but no one does. And anyway, so now we exploit Moore's Law by having exponential growth in number of cores. And we heard about that earlier with the wacky numbers of cores in Titan, right? 50 million CUDA cores, I think it was. So this means there's a lot of uncertainty in the world again. So you guys are coming, kind of coming into your own in a world that's just like the one I did. Moore's Law is kind of coming to an end. Strong scaling has been sort of ignored for decades. There's new technology, new memory technique. DRAM, by the way, what's really amazing is they build cylinders. The capacitors are cylinders that grow out of the top of the silicon in the die with a 20-to-1 aspect ratio. So they're not going to be able to make those at 5 nanometers. So DRAM is going to hit the end of the Moore's Law first. We're going to have whole new technologies that people are prototyping all around the world. You'd like to have the patent on the winner. We have this exponential growth in parallelism. People are making heterogeneous things. Multi-core chips are starting to look like large shared memory systems. Those are going to be heterogeneous. There was worry about power. DOE has a sort of arbitrary 20 megawatt limit they want. And if you think about, if you have like a countable number of dopant atoms in the channel of your transistor, and that's where we're heading very soon, then the probability of them all working every single clock kick is going to start dropping off. So soft error rates are going to go up, probably at least 1 order of magnitude. That literally keeps Intel designers awake at night. Okay, so what if you want more capability? And I would argue that, there's no limit to the capability that humanity requires. If you think that you don't need a bigger computer, I'm happy for you for your small imagination. But there's going to be someone else who has a bigger imagination, right? And there's no limit to it. So and any arbitrary limit, is just going to bound, what we can do in terms of science, right? So if you want to go to the future, you can get a bigger and bigger computer, right? And that's the, I guess, current record holder according to the LINPACK benchmark. You can do something else. You can say, I'm not going to buy a giant dysfunctional, computer that runs the LINPACK benchmark. I'm going to focus on just what I want to do and build a machine that solves that problem. Okay, so that's what David Shaw did. So if you're a billionaire, you can afford to have a hobby, and he got interested in the question of drug design. Got a code called GROMACS from Europe, studied its performance, and decided that if they did this, built a circuit to run this code instead of having a computer, they could be, at the time, 3 orders of magnitude faster. It took, 7 years to do it. But now they're 2 orders of magnitude faster than any machine on Earth, running GROMACS, which they thought was the best code. So anyway, so you could do something like this, or you could kind of start looking beyond CMOS, looking beyond the field effect semiconductor-based electronics that we all use. There are lots of things we know how to do without using computers. A prism, is a Fourier transform machine, right? So a low power one, there's no plug. And so we can do multiplication with amplifiers. There are lots of technologies or other techniques people have known for a long, long time for processing information, but it's hard to get excited about them when your computer just gets faster, right? Write a piece of software and it just gets faster and faster. You never worry about it again. So I think those days are coming to an end, and we're going to start revisiting things like either custom circuits or lenses and other weird physical phenomenon. By the way, when people have these lists of exascale challenges, and you've been hearing, again, a death march of these, I think the biggest challenge is going to be algorithmic, right? If you've got billions of threads, what happens if you have a dot product in a math algorithm where you need to find a Courant number, right? Those things are going to be really damning Amdahl fractions. Okay, and just a few words about specialized systems. There's nothing particularly new here. In the 20s, someone invented machine cryptography, specialized systems. You wouldn't have to make your encipher things by hand. A decade later, Poles invented machine cryptanalysis. So it's done in science. Right? There's the commercial machine we just talked about, but there are also science machines, right? So QCdoc is a machine for quantum chromodynamics. IBM built it. There are several universities involved, and Brookhaven National Lab involved in the design of the machine. This one's actually at Brookhaven, but this is a US one, and this one's a collaboration with the Japanese. So there are several copies of it. So anyway, so these things happen in science. They probably more and more will happen in commerce. So I like to think that imagine it's like 1950, and Bill Shockley and his friends at Bell Labs have made a few dozen transistors lovingly by hand, right? And they're probably really flaky and all this stuff. And IBM's got a factory turning out a tube a minute, 3 shifts a day, right? And you wonder, how can these transistors ever run that down? So a guy, one of the geniuses of the last century, a guy who was worried about the energy constraints on computing in the 1950s, right? So 5-6 decade head start on the rest of us. He was asked by his management at IBM, go check out this nonsense in New Jersey and report back. And he wrote them a memo. It's nothing to worry about. What's funny is, I met him near the end of his life, and he told me that memo was precisely correct about the first transistor, but not the second. And so, so I think we're in this window of time now where things are, changing very rapidly. Not in the semiconductor business; that's very mature business, but in other areas, in particular quantum computing. And so, what I'm going to talk to you about for the rest of the evening, might be the first transistor, it might be the second. I don't know. And that's actually a really fun thing, because if you ordered a replacement Chimera, we could probably asymptotically predict what's going to happen, right? But here, I don't know what's going to happen. Okay, so this is a collage from D-Wave. The thing on the left is a big black box. I have one literally in my garage at work. It's about 12 foot cubed. The black cladding is on top of a Faraday cage. So you see these in labs, low temperature physics labs all over the world. They look copper because nobody puts the pretty cladding on it. They don't have investors to impress. If you open the door, which I don't do anymore because someone tripped going in there and damaged the RF shielding, then you see there's a can for a dilution refrigerator. It's about yay big around and yay tall. If you take that can off, and you have to once a year to clean nitrogen out of the helium traps, then it looks like this on the inside. Let me go to the next one. What I love about this one on the left is look at the temperature, right? So basically liquid nitrogen at the top of the refrigerator. Everything below 4K is all superconducting electronics. And this processor, mine's running at 18 millikelvin. Last year, when I had a previous generation, so I've had one upgrade so far, we averaged 17 millikelvin. Now, there are experiments in labs where people would go colder than that, but no one stays down there 365 days. So it's possible that, unless there are space aliens out there who know more about low temperature physics than we do, that could have been the coldest place in the universe, integrated over the year from New Year's to New Year's Eve, right? It's kind of incredible. And it's kind of incredible you can deliver a machine like that, a helium-3 dilution refrigerator. By the way, you need an export license from Canada. We had to send them a note promising no nuclear weapons research. But it's incredible that you can ship something like that and leave it unattended for a year. Okay, so what does it do? I should have a better picture of this. But imagine you've got a vector sigma transpose. You're multiplying it times a matrix H. then times the vector sigma, right? So it's a quadratic function, and you give it h, and it gives you back the sigma that minimizes that product. That's what it does. It's analog quantum hardware to do that. So this sort of expresses it as a as a sum of, just as sums, but it's basically the product of the vector transpose times h, the Hamiltonian times the vector, and that Ising model is a NP-hard problem. The way they do this, by the way, don't ask me any hard physics questions because I'm an electrical engineer. I didn't take quantum mechanics. I'm sure there are physicists in the room. We can refer the audience to themselves. What they do is first you figure, okay, this thing's made out of superconducting quantum interference devices, or SQUIDs, so a Josephson junction kind of thing. So you figure you've got a magnetic ring, you have niobium, and you're going to have a spin up or a spin down, depending which way the current's flowing around it. So what they do is they put what you could imagine as being like a big transverse magnetic field on it, so it's not up or down. It doesn't know where it is, and that's this term A. And so I put all these sigma, all these qubits, in a state of superposition. Then I back off on that, and I amplify the problem you really want to solve. And when you start out with everything in superposition, your answer's in there somewhere, right? Along with 2 to the 503 minus 1 other possible answers, right? What you're hoping is when you're done and you freeze the system over here, you come out in the ground state, the low energy state. And if you only have one of those, then that's your answer. So this picture kind of illustrates the core building block they use. They've got, so you think of these niobium rings, but the ring is really a rectangle, and it can be sort of any arbitrary shape. So you've got 4 of these things and 4 that overlap. Where the blue dots are, you're looking for your magnetic flux qubits to have their quantum interaction, and each ring has a flux up or down. This is a picture of it. The logic in here is single flux quantum, same stuff from HTMT, by the same guys from HTMT, and you can kind of see the big qubits here and horizontally. Their version of Moore's law: shrink the Josephson junctions, shrink the SQUIDs, and then make more of them. These guys are operating right now at quarter micron lithography, so they're, in some sense, they're an order of magnitude behind the silicon people that they're drafting on. This is niobium sputtered into the glass of a normal semiconductor process. So it's quite plausible that they can continue. Again, they're drafting on the silicon to people. They can, should be able to do this to maybe like 10,000 of these qubits on a chip. I'm sorry, 100,000. So this is the picture of the topology of the machine that's in my garage. Each one of these little sort of rectangles here is one of those things I showed you a minute ago. And then if you're like a vertical qubit, then you're connected to the guys above you and below you. So worst case or best case, you have 6 connections anywhere in that machine. That's actually a very big flaw. So one problem is you have this niobium loop. You lower the temperature below 9 Kelvin, it becomes superconducting. If the Earth's like overwhelmingly powerful magnetic field had induced a little current in there, it's still there, right? That's awkward. So they have lots of little Josephson junctions to try and tune for things like that, but there's a limit on how much they can do. So some of these qubits are dead just because of random magnetic fields. If you warmed it up and cooled it down again, you might fix those, but some other ones might go bad. So it's sort of a random process. A few of them are also off because, just like with semiconductor devices, you sputter material all over the chip, there are going to be small variations. They can tolerate about a 3% variation before they have to, the device is out of spec in this big analog thing. So I have 503 qubits. There are 9 dead ones. In the first generation machine I had, we had 20 dead ones. So their quality is improving dramatically from one generation to the next. This is their version of Moore's law. I had this machine and then top one in my garage. So they're every 2 years they want to quadruple the number of bits. That's the path they're on right now. And their mantra is more bits, more connectivity. Make that graph richer than just 6 neighbors, and more precision. Basically, the thing is you program it by having a bunch of superconducting digital analog converters. So how many bits of precision is there in your DAC? They got to increase that. There's a funny thing. This is an investor. It's private money. They've got salesmen. They've got other investors, and their management tells the people, we don't do stinking physics experiments because that's, whoever buys these things, American Airlines or something, is going to benchmark it, divide by dollars, and pick it if it wins, and they won't if it won't, right? So they don't, waste time and energy trying to do physics experiments to convince the rest of you that it's actually a quantum device. So it's just a business decision. So that's good for me, or for people I employ, because I'm not smart enough to do this. it's good for them because then they can try and find evidence of quantum behavior and publish papers about it. So this was our first quantum signature where we tried to say, okay, if it's not doing quantum annealing, it's got to do something, so let's posit that it's doing thermal annealing. And so Sergio Boixo thought of this really clever little 8-qubit problem. So this is a ferromagnetic problem, so all the black edges are -1s. And then there's an applied field of -1 on the blue dots and +1 on the red dots. And again, that's the equation it's solving on the top. And if you do this, then it turns out that if the 4 blue ones are all +1, then it doesn't matter what the tips are. So there's 16 states here that all have the same low energy, right? So of the 256 possible states, those 16 with that small Hamming distance all have the same degenerate ground state. And so does this 17th one. But because these are all -1s, in the solution space, this one's isolated far from the other ones, if that makes sense, right? So if you think of it as a thermal machine runs simulated annealing, and kind of no matter what schedule you pick, it makes sense that the one that's isolated has 8 neighbors that can fall into it with 1 bit flip, right? The other guys only uniquely have 4 neighbors that can fall into them. So you're going to find the isolated one more often. So this is any one of the 16, right? So you'll find one of the 16 more often, but it's the odds of finding the 17th one, and it's higher. And it's going to be higher kind of independent of the schedule you choose. If it's doing quantum annealing, then there's a funny phenomenon. So these guys here, some of them actually, are the ground state. That's the low energy state during that adiabatic transition. And that should say delta energy on the left, right? So a funny thing, physicists in the room can explain this, but you could say because of E equals mc squared, instead of saying joules, you could use grams. Physicists used to like to use gigahertz. So there's energy because this machine's at 18 millikelvin, right? It's not a perfect quantum device or perfect, so there's an energy gap that's about this big, but there's an energy gap between this and the ground state in this transition here that's much bigger than that. So if this is an adiabatic machine, it should never, if it's a perfect adiabatic machine, it should never see the all -1s. And of course, it's not perfect, so you'd expect that to be wildly suppressed relative to the others. And lo and behold, it is. So this is basically the top dots are the expected value or the probability of finding any one of the 16, and down the boxes down here are the probability finding all -1s here. If you think that, well, it's biased toward +1, then this one here, he's just inverted the problem, and here he's moved around the chip, so you've got, there's no magic part of the chip either. Anyway, so this picture here, this thing just got published last month, but the result's over a year old. There's a long lag between, as you know, right, between finding something and then finally getting it formally published. Anyway, this picture essentially changed the conversation in the United States about D-Wave from junk science, right? A government program manager told me once, Bernie Madoff is in jail. Where is the justice? So now it's gone, so people don't think it's junk science anymore. There's another similar quantum signature. Sergio observed this funny behavior here where if you run like simulated annealing really, really fast, you probably won't get the answer, right? If you run it really, really, really slow, you probably always will get the answer. And if you have something in the middle, you'll get kind of like a Gaussian distribution, which is this red thing. So with the D-Wave, where we're seeing this funny bimodal distribution. And so Matthias Treuer, who's an ETH professor, I don't know if anyone knows him, he saw that, talking to Sergio, saw that and thought, So he did simulated quantum annealing with a path-integral Monte Carlo code, and lo and behold, he reproduces the same bimodal distribution. And then if you do gauge averaging to sort of deal with noise in the machine, these look pretty similar. So that's up on the archive. So they're trying to publish it. Anyway, so that's the second kind of bit of evidence that the thing really is a quantum device. It's not some thermal device. I should add some guys from IBM. The obvious thought is, well, we posited thermal or quantum. What if there's a third? Some guys from IBM actually had an archive post recently suggesting a third. So we don't think it's that third, but one of you tonight maybe will think of a fourth. But until one of you does, I'm claiming it's a quantum device. We have an algorithm and the data for a witness for entanglement. What we need is a really big account on a really big computer in order to compute it. Okay, so how fast is this thing? Because at the end of the day, it's cute that it's the world's largest, sort of man-made quantum engineered device, but will it do anything useful for humanity? So if you make some random glasses in the topology of that machine, you call Cplex, then you can see kind of timing going up exponentially. That's a log chart as you add qubits, and they're plotted on square root so that the curves look straight. we wrote a belief propagation code that was sort of specialized for this problem, so that's the red thing. What's weird is if you turn it from 1s and -1s to 1s and 0s and make it cubo, Cplex is a lot faster. I don't know why that's different. Anyway, the problem with those is if you let Cplex run long enough, it's an exact solver. It will find the answer, right? So it's, in some sense, what you really want to do is, whereas the D-wave is a stochastic machine, it may never find the answer. So a straight up comparison isn't to Cplex, or it's to something that's also stochastic, like simulated annealing. So in this case, Matthias Treuer, you hire like the world's smartest Russian postdoc and have him write the world's best simulated annealing code, then this is how that code performs. And basically, each line here is what is the median time, infinity throws the mean off, so median is a better measure here. What's the median time to, in the bottom case, having a 99% probability of seeing the answer 1% of the time, and in the top case, a 99% probability of seeing the answer 99% of the time. So these are just sweeps to estimate how long you'd have to wait in order to solve a problem. The dotted lines are measurements from the D-wave. You can't have it run in less than 20 microseconds. So this is artificially high here. So you can't look at the slopes here and compare them, but you can kind of maybe look at them over here and compare them. So it looks kind of like a tie. If you're optimistic, maybe you say, hey, the D-wave is starting to pass down there. So then you have a really smart Danish postdoc who ports it to a GPU, and it looks like a straight up tie, right? So this is kind of one quantum chip versus one, CMOS chip. And we can quibble about the amount of investment and all this stuff. You won't get a lot of, we're talking microseconds here, right? So you're not going to get you think about MPI overheads, you're not going to scale this to too many other processors, right? So anyway, so the important part you're seeing here is, I'm claiming it's a quantum device, but I'm not claiming any speed up. No one has claimed that they've seen quantum speed up yet. Of course, people are trying to find it, and their intuition as to where to look. But in these millions of randomly generated glasses, no one's claiming speed up yet. Okay, assuming and this is why I tell you, I don't know whether this is going to, what the future is. If no one finds speed up, then this was, an interesting experiment, but it'll be a failure in the end. But if we do find speed up, then where would you look for problems? So here's from Wikipedia a list of places you might look. Here's a list of things I know about that are going on. Lockheed Martin got into this because software V&V, not writing software for airplanes, but V&Ving the software someone else wrote for like the flight control system. It's a quarter of the NRE of the Joint Strike Fighter. It's growing exponentially from one plane to the next. The guy who's the chief scientist likes to say, there's this joke that the Air Force someday will spend its whole budget every year on one airplane. And he says, no, that airplane is going to be a loss leader. We'll give it to them to get the V&V contract. So anyway, so that's Lockheed's killer application. They're also interested in other optimization sorts of things. What's interesting is a guy at Google named Hartmut Neven is interested in, his job is to tag Google Earth because it's too big to do it by hand, right? So you got to have computers do it. And so you have to think of, what they call strong classifiers to recognize objects, right? So if you're looking for, Ferrari, it's red, it's, 20-ish feet long, it's got 4 round things on the bottom, right? And a horse on the back. Anyway, his job is to find those strong classifiers and then, send it off to their big cloud servers to actually, troll through all the data looking for whatever. Justin Bieber or other important things, right? So in 2007, he heard about D-Wave and he thought, quantum annealing, it's just another heuristic. Let me try quantum annealing. And you can simulate it. So he tried quantum annealing and wrote a paper saying, hey, this is better than AdaBoost, right? Which is something they've got in production. So he found his killer app, and it took him 3 tries writing proposals to get his management to go for it. But he's going to take delivery of the second D-Wave. They're installing it now. His partner is NASA Ames, is actually going to Ames, just like Lockheed's machines at USC. And that'll be the first. Anyway, this is Google's killer app, is image processing. Again, software V&V for Lockheed. There's at least one professor I know at Harvard, just got tenure, who's interested in sort of image processing of chemicals. He's looking for organic photovoltaics. I also know someone interested in like sensor assignment and tracking. Those are classic NP complete problems for missile defense. So that means that everything else you guys think of that are hard problems are wide open territory that no one's looking at yet. Here's my favorite little thing. So I like to do linear solvers. but direct method solvers instead of iterative solvers like the rest of you are probably familiar with. So I write a solver that's in a code called lsdyna. So here's an example of just the time spent running on a real problem. So this is almost an hour, but 43 seconds, roughly 1% of the time was spent reordering the sparse matrix. That's an NP-complete problem, and there are no good parallel heuristics. I used METIS, you could use Scotch, but if you thought, well, use par METIS or PT Scotch, the parallel versions, you don't get as good an answer. They run faster, but you improve the 1%, but you make the other 90% worse, right? So it's not a good trade-off. So if you're a mechanical engineer, then this is a mathematical bottleneck that you're stuck with right now until someone comes up with a better idea. So what people do is nested dissection, chop the problem in half, and then recurse. It's an NP-complete problem. There are lots of heuristics. We've had half a century to invent heuristics. So ones I know people have used are level sets. George and Lou published a big paper like 30 odd years ago. Ashcraft and Grimes are doing something right now. Moments of inertia, MEs thought of that. Fiducia Matisse, double E's do that. Spectral bisection, Horst Simon from LBL did that, if anyone knows Horst. He knows Horst. Yeah, you work for Horst. There are other algorithms I don't know of anyone trying, right? Simplex method, interior point method, those are big in the, my brain, oh well. Anyway, those are huge. Simulated annealing, I don't know of anyone using that, or quantum annealing. So here's my little experiment with quantum annealing. The idea of saying, okay, I want to partition a graph, can I even express that as an Ising problem, right? Get in this form this machine can think about. So that's an old idea. There are a bunch more that have been found recently. The author of this doesn't want to bother trying to publish it. Anyway, the bottom line is, well, there's a funny way you program this thing. And there's no Fortran or C or Ada code I've ever written that's organized like this. You're finding a minimum energy solution. So what you want to, and you want your solution to be the minimum energy state in that quadratic form. So what you want to do is think of all the wrong states and apply and give them penalties so that they have higher energy. And then, hopefully the machine will just skip them and go to the low energy when this is your answer. So it's a weird way to think. So here's the formula for graph partitioning. On the left, what you want to do is you want to say, I want an equal, I'm going to find an edge separator graph. So I want half the nodes to be positive spins, half the nodes to be negative spins. If you just summed all the sigmas, then all minus ones might seem lower. So you square the term, and presto, if they're half and half, you'll get 0, and 0 squared is lower than anything else squared, right? So that's one thing. Get a balanced partition. Then the other term says, if I have an edge connecting the two domains, then penalize it. So basically, I multiply all adjacencies. Basically, find every edge and multiply. You can make B a 2, and that goes away, and throw away the constant term because you're just optimizing. And then here's a trivial example. So this is about the simplest graph I could think of, right? So here's the matrix. It's all ones because of the first term, and then the zeros because minus ones came in where there were edges. And there are 8 possible solutions, and lo and behold, you multiply that out, and you find that the ones that have 2 of one, 1 of the other, and only 1 edge cut, all come out as the degenerate ground state. So if you have no partition at all, or you have too many edges cut, then your solution is higher energy. So this is the mapping for a slightly bigger problem. This is just a line of 10 nodes. I like this chart because it illustrates an awkward problem. So you're going to create the Hamiltonian, the H for the problem you want to solve, and they've built the graph for the machine for the H that they implement in hardware. Getting your H into their H is called subgraph isomorphism, and that's an NP-complete problem, right? So it's a really hard problem, and it leads to the notion of recursion, right? You use the D wave in order to program the D wave, right? But if you do that, and I had a student do that for me because I haven't managed to do this for myself yet, then you run a bunch of trials. Remember, the machine's stochastic, so it doesn't always give you the right answer. But what you find is the low energy state of 5 ones and 5 minus ones, or 5 minus ones and 5 ones. Those come out. This thing here is almost as good because there's only 1 edge, and the balance is just slightly off. And these ones aren't so good because the nodes are balanced, but there's 2 edges cut. Maybe you can see there's some wrong answers in there, so you better have a good secondary test to recognize if you really have the right answer. But the low energy state is the one you're looking for. So another problem with the direct mapping is they only have 6 coefficients, and if you have more than 6 or the wrong set of 6, then you have to sort of inflate your matrix, make it bigger to find all the missing edges. So worst case, you need n squared vertices in order to map your Hamiltonian to theirs. So people have tried to think, well, you want to get around the n squared problem, and it's too hard to do this anyway. So can we have heuristics that maybe find a answer to a close problem and then kind of iterate and converge on yours? So the manufacturer makes one called the black box. So here's a slightly bigger matrix. This is already too big for a direct embedding in the current machine. And of course, real problems have many orders of magnitude more equations in them. But anyway, if you let this thing iterate a while, you can find a low energy solution. We don't like it, so we have our own, which is this red curve. So it kind of comes down faster, but they both converge about the same. Anyway, so that's another research problem that's going on. Okay, so let me summarize. You guys can head for the bar. I'm sorry?
Maybe yes, maybe no.
Oh, the audience is going to get hostile. Okay, so I think this is really cool. So it's the idea of a quantum computer was first posed in 1982. People got excited about it, I think, in 1994-ish when Peter Shor published his algorithm for factoring composite integers. The idea of an adiabatic quantum computer, that didn't even come up until 2000. Eddie Farhi and colleagues at MIT came up with the idea. So it's literally been only a dozen years since physicists even conceived of the idea until people are out there trying to make these things. It's really a remarkably quick time. So of course, we're looking at it with Lockheed. I think a guy named Ned Allen at Lockheed deserves special credit for kind of the intellectual courage. He had MIT professors telling him, "Don't do this; it's junk science," and he went ahead anyway. Anyway, so we're studying it. It might, that's the key word because we don't know yet. It might be very powerful. Maybe in as little as 2 years when the next generation comes out. But it's not obvious, what problems it would solve. There's a lot of open research here. So, again, it's at 18 millikelvin. It's an open system. It's not even obvious why this thing works. The MIT professor who invented the circuits they're using didn't bother to patent them because he knew from the theory they wouldn't work. Why would you file a patent for something that's not going to work? No one's found quantum speed up yet. And even if you can find quantum speed up for some set of glasses, then we've had half a century to think of things like the simplex method. So if you try and go to a real problem, how do you know that the simplex method just won't be a better algorithm, right? So that's an open question. There's no Fortran for this thing, right? So if you were programming a computer in 1950, there was no high-level programming language, right? I started programming computers in hexadecimal because I was designing. I'm an electrical engineer. I was designing them. I knew what the wires were for. I didn't need an assembler, much less some stinking compiler. And when a guy got an award for writing assembler, we went out and drank beer and talked about what a wussy he was, right? Anyway, so this is someone needs to invent Fortran. What's the topology of the machine? It's probably got to be richer than the one they've got, but no one knows what the right answer is because, again, no one has a real application. The guys at Lockheed would like triangles in that graph. There aren't any triangles in that graph. And the other thought is, D-Wave is the first adiabatic quantum device. It's not a computer. It's an adiabatic quantum annealer. It's just a one-trick pony, like a lens is a one-trick, Fourier transform machine, right? It won't run Windows. But anybody else who comes along, and there was a $10 million LDRD at Sandia, so there are other people thinking about adiabatic computing, and Sandia was trying to think of a real computer, not just an annealer, but they're going to face a lot of these same problems, right? They're going to, whatever their qubits are built out of, they're going to be in some three-dimensional space, and they're not going to talk to more than their neighbors. So they're going to all have the same kinds of problems. It's an optimization machine. It suggests there's maybe a richer space of quantum optimization. Again, this is Google's killer app. Of course, there's real adiabatic quantum computing, so even an adiabatic quantum annealing isn't what people have been looking for to solve Shor's algorithm. I guess that's this point. Oh, Andrew Landau at Sandia was trying to make an adiabatic quantum computer, and that's not the same as a circuit quantum computer. So last thought, I think we're entering a really exciting time. It's not obvious what high-performance computing is going to look like in 10 or 15 years. I think it'll look quite a bit different than it does now. I think that as we build things like Tianhe 2 or 3 or 4, bigger and bigger and bigger, they're going to get fewer and fewer applications are going to run. They're going to start looking like Anton for material science. And I think that's great for you guys. It's opportunity. You can build careers on it, invent all sorts of things. So, done.
Thank you.
Questions, comments?